All right, well, questions before we continue with the review? So I forgot to mention $* yesterday when we were talking about variables. So $* is just everything that you typed in on the command line as a single variable. It's $1 followed by $2 followed by $3, etc. And that's handy sometimes in a script to be able to pull up. So that's all that $* means. All right, so we went through Zenity, GCC, GDB. So let's talk about makefiles. So let me do a sample makefile. Oh, that's not exciting. We haven't really talked about the find command. This isn't on the test either, but find is a useful utility for searching recursively in subdirectories. I'm just going to make a makefile. So makefile, remember, it's this pair of lines. First one is a target and a list of dependencies. And the second line begins with a tab. It's got to be a tab, not spaces. And it's the command for creating that target if those dependencies are satisfied. Alright, so whatever your GCC command might be, maybe I want a -g switch in there or whatever. And it's just pairs of these lines, so main.o, if it doesn't exist, it can be built as long as you have a main.c. And the way we build it is by saying maybe gcc-g-c main.c. And sub1.o maybe depends on sub1.h or sub1.c. And some include file I made called all.h. And maybe the way I compile that is gcc-g-c sub1.c. And maybe that's my pair of lines for function.o. And so if you have none of this stuff except your source code files, right, none of main.o, sub1.o, or func.o exist, and so it looks for recipes for those. Main.o can be built from main.c. Here's the command to build it, so it'll execute this command. Same with sub1.o, can be built from these, and here's the command. This is a list of dependencies, okay? These are not necessarily the things that have to get compiled in order to build sub1.o. All.h does not appear on this GCC line, right? Just like we don't list stdio.h, even though we're including it. To compile sub1.c, we just say gcc sub1.c, right? And with a -c switch to make it into an object. But nonetheless, sub1.c, if it says include all.h, it depends on all.h in the sense that if all.h is missing, we cannot execute this command. And if all.h has changed more recently than the last time we did this command, we have to execute this command again. Okay, that's the information that we're coding on these dependency lines. But then the compilation line is just, you know, the plain old compilation line. And it could be that I have all.h listed as a target, right? And maybe I'm doing something weird like this. You know, maybe to make all.h, I need to have these 3 other .h files. And if I have all of those, then the way that I build all.h is to take those 3 files, cat them together, and output that to all.h. Because maybe the way I live my life, I like to have my function prototypes in a separate .h file from my defines and from other stuff. But I don't want to have to number sign include those 3 .h's. Well, my make file is set up now so that if I just say make, and I happen to change, you know, defines.h, it'll go ahead and it'll rebuild all.h. And then it'll say, oh, I've got to recompile sub1.c, and sub1.c says include all.h. It'll go ahead and pull in that new combined.h file. So make files don't really care what you're doing. They just blindly follow this recipe and do whatever it says. Yeah?
Is it a library switch up in the LM?
Yeah, I was just assuming I'm using the math library somewhere.
Wouldn't that just tack on, yeah, wouldn't that just tack on all that stuff in the prototypes.h, defines.h, and others.h? Wouldn't that just tack all that on to the end of all.h?
Greater than will actually zero out all.h first. Right, so 2 greater thans, yeah, that would tack it on. Yeah.
If you had a folder containing all your .h files, what would that look like?
Yeah, so like that.
Okay.
Cool.
Alternatively, there could be the wildcards, as long as those are the only files.
As long as those are the only things, yeah, I could just cat star.h into all.h. I can't wildcard the dependencies, I don't believe. And the wildcarding is really convenient, sometimes potentially dangerous, right? But yeah, that would work.
On the cleans, I was able to get it working for my make file, no problem, but I was just wondering how they work, because it doesn't seem like there's no dependency there. So is that just programming how make files work?
So if I say something like clean, typically I don't have any dependencies, right? And I would say rm, yeah. Now I could say, you know, if I have all these .o's, then remove them, but then if I only have one of them, clean wouldn't remove it. But really we're just saying, you know, if I say make clean, do this, right? Doesn't matter what files exist or when they were updated and so on. And we probably want to remove main also.
So how does it know to actually go to clean though? Because the way it works, I believe, is it goes to the first one, checks all the dependencies.
If you say make, it will try to make the first thing, which is main. But if I try to say make clean, it will just look for that recipe that's titled clean.
Okay.
Right, but you have to.
It's not gonna automatically.
It's not going to automatically do it. Yeah, in fact, in here, there's no way that clean is ever going to get executed unless I say make clean. And then maybe there's an install line which says copy main to /bin. Alright, so now if I say make install, and if main exists and is up to date, it'll copy it into the binary area so that other users can access it. Yeah.
And so I think you were talking about this earlier, but when, like with clean, where there's no dependencies, that means it will only run that command if you specifically tell it to?
No, I mean, I could have, right, I can get rid of this dependency, and any time that it needs func.o, right, it will go ahead and it will try to run this GCC command, right?
So then making a command that you can only or will only run if you explicitly tell it to run, is that something then just special about clean? The name clean?
No, it's because nothing in here asks to build clean. Nothing is listed as depending on clean,
Okay.
right? So I could call this whatever I wanted. But since nothing in there, says, well, I need to build clean in order to continue, nothing is going to build it.
And a voting target would be when you set something up to be the main one that's not actually on the top line, right?
A what?
They're called voting targets, where you say,
Oh.
you could have, I think, I don't understand it very well because I've never done it.
Mm-hmm.
I think you can have, say you wanted func.o to actually be the one that checks. So like say you wanted main to be the middle, you can actually define, you can arbitrarily say I want main to be the one that's the target.
Okay.
I think that's how it works.
So I mean, if main's not at the top, I could say make main, and it'll build that.
Okay. So you can actually put like a line of code.
Oh, something in the make file?
Yeah, this
Okay.
make file says like dot voting target equals.
Oh,
whatever
okay.
you want. So
I have-
you could, I guess, make it clean.
Yeah,
Say
yeah.
make, and then you could say.
Okay, cool. Yeah, I haven't played with that. There's a whole lot more to make files than what we've gone over. And if you look at some of the kind of industrial strength mass make files that you get when you download stuff, they can get pretty overwhelming.
But yeah, there's the voting I was talking about.
Yeah, definitely install. Interesting. Simple makefile is a unicorn. There you go. Alright, well, this is one of these things that I stumble across all the time, whether I want to or not, but I don't have a handy example I can pull up. But if you download something from the web, like a driver for a device or an API for something, right, it usually comes with a makefile. And they're big and long and complex and usually set up so that they work in a wide variety of situations depending on what type of compiler you have, what version it is, what your architecture is, how multiple byte integers get stored, big order, little order, and they grow into this whole kind of language and environment in themselves. But we can usually get away with just, the basics. And as we said for PA4, right, you can get away with something as simple as that. That's like the simplest makefile for building a target called main. And it's really just, if main.c is more recent than main, it'll say gcc-o main.c. But usually you have a project split into pieces. You want to be able to do more tactical compilations. All right, so make files, and you just say make, and it makes your targets according to the recipes. Tar, we haven't had to use tar because we've been uploading through Git instead of Canvas. But there's only really 3 tar commands I teach people in here. Tar cvf archive files, tar extract vf archive, and tar table of contents vf archive. So make an archive, pull things out of an archive, or look at the contents of an archive. And it's a unique Unix command in that it does not take a dash on this set of specifiers for what you wanted to do. Most things you put a dash in to specify switches, or 2 dashes if it's a long switch. Tar just takes this collection of letters. But the behavior is if you do this a few times, it's pretty self-explanatory. So there's a bunch of stuff in here, and I want to put all my source code, my C files, into an archive. Alright, tar cvf, the name of the archive, and then the list of files that I want to put in there. And the V is telling it to be verbose to show me what it's doing as it does it. So it lists all the files that are added in there. If I do tar cf, then it acts silently. But now I have this file called source.tar. And if I do a tar tvf source.tar, it shows me the contents of that archive. And it looks a lot like what happens when I say ls-l. And now I can move this into a different directory. So now I'm in a new directory under my home directory called work area, and I have my one tar file, which is source.tar, and I can look at it again. If I want to extract files from there, it's just tar xvf source.tar, and now I have all these files sitting in my directory, and they have exactly the same creation date, creation time, ownership, permission bits as they had when I made the archive. Right, it remembers all this stuff. So I can take source.tar, I can put it on a flash drive, or I can FTP it, or I can email it to someone, or I can push it to Git, or whatever I want. And it's one file that has all of this stuff in there.
What's the pro and the con of tar versus a zip file?
I don't use zip files, so I'm not sure. But I don't know if they record all this information. Because zip files originally worked under FAT file systems, I think. which was Windows. And so goofy file names might trip it up. But let's see. So there's some files with weird names, and there's some files with different permission bits. Right, so all that stuff is saved in my tar archive. So zip, where's the output file go? Next. I spelled weird wrong. So there's my data.zip. So let's move this stuff into an old area. And let's extract from data.tar. So our files are there, they have permission bits, they have the ownership. And so unzip seems to work the same. So I don't know if there's a big difference. Maybe unzip's better than I thought. But an interesting experiment would be to try to unzip this under Windows and see what it does. Yeah, it's a good question. Tars are most commonly used with the Linux. I don't know if that's just a legacy thing or if there's a fundamental advantage. Alright, so to our regular expressions, I'm not going to go over regular expressions because that's a whole lecture in itself, but I think I posted a cheat sheet for those. Regex summary. So that's the Reader's Digest version of regular expressions. Anchors, a few wildcards, throwing things in registers, pulling things from registers are pretty much the main things. Throwing things in brackets to match any of a few. That's probably plenty for what we're doing this next week. Sed, again, main thing for sed, just kind of, I would say, know about doing these substitutions. So you can say something like sed, quote, substitute old, new, and then you can have an input file, or you can just feed a file into standard in, and it will apply these substitutions and generate the output to standard out. If you come away knowing that much about sed, it was probably worth coming to that lecture. But sed can do a whole lot more. Awk, here's one line to know for awk. right, this prints column 3 of whatever file is. So read each line. The $3 says print out the third field where the fields are separated by spaces. And if you want them separated by commas, you can say -f comma. If you want them separated by colons, you can do -f colon, and so on. So you can specify the separator. And awk, we saw a whole bunch of things we could do, including programs, associative arrays, and so on and so forth. But this by itself is a pretty good carry away message. Yeah.
Is that second single quote on the awk statement, is that that's inside the bracket?
Thank you. And I don't believe I posted a cheat sheet for awk instead, but yeah. But those are good enough for now. All right, bash programming, start with a shebang. You put in comments by putting in a number sign followed by anything else. It can be at the beginning of the line or later in the line. Special variables that we already talked about, including $? Variable assignment, variable equals string. That's the variable equal to that string. Make sure you know the style of if-then statements that we've been talking about, because again, these are what I'm going to want to see in bash code that you write for the exam. So while loops, while bracket bracket, condition bracket bracket, do statements done, right, with mandatory spaces in there. Comparing strings, use double equal or exclamation mark equal. Comparing numbers, use -eq, -ne, -gt, and so on. Right? Looked like everybody nailed this on PA5 when I was looking at people's code, using the right operators for strings and numbers, so that's good. Put these things inside double quotes just to be safe. Numeric comparison, use those binary operators instead, but again, while space, bracket, bracket, space, condition, space, bracket, bracket. If you want to do logical operations on expressions, you can put them in between the double brackets. So double ampersand for and, double pipe for or. That's very C-like. If statements, same thing. If, bracket, bracket, condition, bracket, bracket, then, and then phi for the end of the if, or if, then, else, conditions phi, or if, then, elif, condition, then phi, and so on. And then for evaluating expressions, use this $paren, and put your argument inside, your expression inside. And don't worry about checking for legal numbers. I don't think I asked you to do that on the exam. While loops, variable assignment and interpretation, $paren, read and echo. We know about algorithms, right? So don't memorize your solutions to ODPs or to programming assignments, right? Think about how you come up with the algorithm and be able to recreate that, because you'll be coming up with algorithms that you haven't done already for this course. But small pieces of things, right? Things that involve looping and doing conditionals and stuff like that. And then C programming. So basic syntax you should be fine on. Characters, right? char space variable name makes a single character. If you want to represent a single character, put it inside single quotes. So single quote A is the character A. It's basically the integer 65. It's ASCII code. Where strings go inside double quotes and then they become addresses of the first character in an array of characters. Make sure you know how to write comments in case you want to comment your code. So / is a single line comment. Number sign include file name basically reads the contents of that file and loads it into your program. Right? These happen before any compilation takes place. So if I say number sign include blah, the compiler will open a file named blah, read the contents and load it into my input file in place of where I said include blah. And that's actually before we start compiling. That's something called the preprocessor. The preprocessor gets this huge file that has all the code for stdio.h, all the code for standardlib.h, all the code for myfunctions.h. And so it's this big augmented C file that gets handed to the actual compiler. All right, so anything in those include files basically becomes part of your code. And if you include inside angle brackets, it looks in certain default directories. Because standardio.h and math.h, we don't have those in our directory usually. They're usually under user lib include or user include sys or things like that. So there's things set up that say if you see angle brackets, where should I look for these include files? Whereas double quotes just looks for exactly the file you specified. Arrays, main things to know about arrays, they start from element 0, okay, indexed from 0. There's nothing about an array that tells us natively how big it is, okay. Avoid using size of on arrays, because in a few rare cases it can actually tell you how big the array is, but in general it can't. In general it will come back with an 8, which is the size of the array, because the array is a memory address where the first element is found, and memory addresses are 8 bytes. So size of a 2000 element array will usually return 8, and if you use that, then you get bad results. And the other thing about arrays is that they have multiple masks that they can wear. So you can say double data 1000. You can say double asterisk data. Both of those are declaring data to be an array. Right, this one allocates memory for 1000 doubles and has data point to that. This just says data is an array of doubles, but it doesn't give it a value. It doesn't allocate memory. But in our main program, we usually want to allocate memory for an array, so we would do something like this. But if we had some kind of function declaration, and we just know that we're getting an array, but we don't know how big it is, the space is already there, the data values are already there, we would usually just declare our argument as a pointer to whatever type of objects are in that array. But if I know it's 1000 elements, I could also declare this to be a double data bracket 1000. So that's what we did in PA4 usually. So those are synonymous, and data really means the address of element 0 in this array. So if I say size of data, it's going to give me the size of this address, which is usually 8 bytes. .224 we should never have to use size of. 222 will have to use it for a lot of things, but you shouldn't need it for here. Alright, so character arrays are a special type of array. We think of them as strings. But again, because there is no such thing as an inherent length to an array, we need some way of saying this array contains 5 letters. So we add this special character at the end of a string called a Null Terminator. It's a character with ASCII code 0, and the assumption is we're never going to make a string that we want to have contain an ASCII code 0 in the middle of it. So we can treat it as kind of a reserved code, and we just put it at the end of the string. And then all these utilities, string length, string compare, string copy, printf, live with that assumption that I'll just keep looking at elements of the array until I find this null character. And I'll say, okay, the string just ended. So it's just a convention. We could use the letter Q as a null terminator if we wanted, but then we couldn't have strings with the letter Q in them. All right, math.h we need if we want to do things like trigonometry or square roots or exponents or things like that. String.h we use to work with string functions like string length, string compare, string copy. I think those are the only string functions that we've really used in this class, but there's a whole lot more in there. C-type is an include file that defines things like is space 2 upper, 2 lower, is alpha num, all of these helper functions. And if you need to do conversions, right, C-type is the way to go, and you get all these functions, is blank, is space, and so on, as well as these things for converting. And yeah, all they're doing is they're monkeying with ASCII codes. If you get something you want to know if it's a letter, see if the ASCII code is between 65 and 91, or 97 and whatever comes after that, 126 or something. And if you want to convert from uppercase to lowercase, you just add 32 and so on and so forth. But they're written for you and provided for you to work with whatever system you happen to be on. So we can do those for case conversions and so on. Remember that something like 2 upper does not change C. Okay, 2 upper reads this and it returns as a function value the uppercase version. So if I did something like this, C2 would be the uppercase version of C. Right? But C is not changed by this. And that makes sense because if I said 2 upper, right, if this actually changed the argument, then my lowercase a would somehow change to an uppercase a, and that would just be weird. Right? You can't change arguments to functions, ever. Right? If we pass the address of something, we can't change that address, but we can use that address to change what the person really wants us to change. So it's the return value. And this is always legal. And a number of people don't realize this or aren't comfortable with it maybe. But you can have something on the right side of an assignment statement and you can put that same thing on the left side. The way assignment statements work, the right side is evaluated. Could be a simple arithmetic operation, could be a function call that takes 10 hours. But when this function returns, whatever that value is, in this case that would get assigned to C. And if C happened to appear over here, that doesn't cause any problem. So you can always have the same thing on both sides. And it's really no different from saying something like this. Right, as opposed to that, which also works, but it's more statements, it's confusing, it's more variables. All right, argc argv. Does anybody want to talk about argc argv? We've kind of talked it to death. I'll give you the 30-second version. First argument is an integer, second argument is a pointer to a character. Okay, argc is the number of arguments, and argv is an array of strings. And we can use argv0, argv1, up to and including argc minus 1. All right, so if argc is 2, then we have an argv0 and an argv1. 2 arguments, right? And those are the name of the program and then the argument that we specified after the program when we ran this on the command line. So if we say main A, B, C with spaces, right, this would have an A, this would have a B, the next one would have C, and so on. So we use those for reading command line arguments, and they come in as strings, and if we wanted an integer, it's going to be a string, a character 1 followed by a character 2 followed by a null terminator. If we want to use that as an integer, we have to convert it, so that's what scanf does. So scanf is a way to take a string and say, you know, I'd like this to be an integer. And if you find an integer in that string, I want you to store it inside this presumably integer variable called var. And because we want this to change the value of this variable, we have to pass the address of the variable. So that's the ampersand. And this will return an integer. And the only way we know if a scanf succeeded is by looking at the return value from it. We had one thing we were trying to convert. We had one variable we were trying to load. So we have to see if this function returned a 1. And if it did, then we know that this variable is valid. If I have a %d, %c, %d, %d, and I list 4 variables over here by address, and I want to know, did it succeed in converting all 4 of those, see if it returned a 4. All right, so the return from scanf is the number of things that it successfully converted. All right, printf is an output function. We didn't do a whole lot with fopen, fclose, flush, fprintf, so don't worry about those. But we'll work with those in 2.22. But that's basically for doing printfs and fgets from things other than standard in. If you want to open a file and write to it, you open it with fopen, and you write with fprintf instead of printf. But you still read with fgetc and fgets. And then you can close it. But I won't ask you about file I/O like that. But you do want to know fgets. And fgets takes 3 arguments. The first is an array to be written. The second is the length of the array. Why? Because again, arrays in C don't have an inherent length. And since we're just passing an empty array that we want to have used to load things into, there's no such notion as using a null terminator to figure out how big this array is. We're not passing it a string. We're passing it an uninitialized string usually. And there's no way that fgets can know, well, how much space do I have in here? So if you type in 1,000,000 lines of text and hit enter, how much text should it load into this array? Well, that's what the length argument tells you. Okay, and this is why fgets is safer than just plain old gets. Because gets, all you do is give it an array. And it'll say, well, you typed 1,000,000 characters, I'm just going to load those in, and it'll start loading them into consecutive locations in memory. And once it gets outside the array, it starts writing on other variables and potentially code and system areas and so on. And if fget returns null, then you know that you hit the end of the file. GetCar, which is really fgetc, but getCar reads a single character from standard in, takes no arguments, And that returns a special flag, uppercase EOF, when it hits the end of the file. So you actually look for this symbol, and that's set up in standard I/O. So fgets, look for a null. GetChar, look for EOF. Writing functions, calling functions, returning values from functions, right? We've been doing functions all quarter. But, you know, I'll have some questions where you're writing a program, I'll have some questions where you're writing functions. So make sure that you know, look back at some of the functions you've written and know how to write a function, right? It's a type of return value, the name of the function, parentheses, list of arguments with the type of each argument. So something like, you know, character, my reader, integer x, comma, car name. So this is a function called myReader. It expects an integer and a character array, and it returns a character. And in my main program, I could say something like, you know, character C. I could say C equals myReader. And I could pass it an integer, and I could pass it a character array like hello, or something that I got from fgets or whatever. All right, so here we're just putting the names of variables or values. Here we're listing variables by name, and we're saying what type of variable they are. Function prototype will look exactly like this, except we put a semicolon at the end. And that says I'm not defining the body of the function, I'm just telling you what the function looks like, what it expects, what it returns. And then the last thing, again, algorithms, just you know, be thinking about the kinds of algorithms you've done in these different assignments in the ODPs. Running sums, setting flags to note that something's happened, but not use that fact until later on. Initializing things, for loops, while loops, if statements, stuff like that. That's pretty much it. That's 224. And I think everybody's in good shape for the exam. I don't think there's a whole lot that you need to study per se for this, right? You have 4 pages double-sided of notes. So if you can't remember the -G switch on GCC for using the debugger, right, put it on your note sheet. You don't have to memorize tons of stuff, but you definitely want to, you know, just get some practice with writing code, simple functions. The mechanics of that can be tricky when, you know, the clock starts ticking for an exam and it's like, I don't remember how to write a main program, you know. So, you know, put things on your notes or just practice some more with them. And I shouldn't be asking you to do anything that you haven't already done or that's comparable to stuff that you've already done. So I'm not, you know, planning to throw any huge surprises at you. So practice a little bit if you want, dust off on some stuff, make some good notes, and I will see you either Monday or Wednesday. Monday at 10 o'clock, Wednesday at 11 o'clock for 224. Make sense?
You can choose which one.
To some degree, yeah, if it really works out better, but you know, if nobody shows up Monday, then we got a problem because we can only fit like 36 people in here on Wednesday, and if there's 55 people wanting to take it, that's going to be an issue. So if you can, I'd say come to the one that's scheduled. And if you come Monday, you get it over with, you know. So that's always good. All right, I will see you either in 2:15 or I will see you next week.